everyone, I'm Stacy, and I'm super excited to talk to you today about Databricks workflows, which I've been working on for the past several years. And Databricks workflows is the orchestrator that's deeply integrated in the Lakehouse. It's there to reliably power all of your recurring and streaming tasks, whether that's ingestion, analysis, or ML. That integration makes it easier to focus on your work. We'll take care of your jobs and workflows. They'll be there to power all the work you care about. Now, we haven't talked as much about this part of the product recently, but Workflows drives a vast amount of Databricks usage. In fact, it's our most used service, creating 10 million virtual machines a day. I've actually heard that's the largest number from any service on one of the 3 large cloud providers. Now, a lot of this is ETL and Spark, as most of you expect. However, there's also a large portion of AI training, inference, and other data science and analytics tasks that already leverage workflows today. In fact, 30% of the workflows we're running aren't Spark at all. 10% of them are actually running anything anywhere on single node clusters, for instance, orchestrating other services or doing file operations. And that's why more than 7,000 Databricks customers already take advantage of the benefits that Databricks Workflows is bringing, because we've made orchestration of data, analytics, and AI easy for them. And here I'm going to talk about 5 of the things that they love about Workflows. It's a fully managed Lakehouse orchestration service that makes it possible for your analysts to build reliable workflows on any cloud. First up, it's not just Spark. We actually orchestrate anything, anywhere. That's SQL, it's Python notebooks, it's Delta Live tables, it's even dbt projects. And you can schedule and orchestrate these dependencies between all these types of tasks across any platform, including our partner services. Second, it's super easy to create these workflows with an intuitive UI. I'll show you that in a demo in just a minute. But this really democratizes data by enabling more and more analysts or analytics engineers to run demanding workflows in production easily. That gives data engineers the freedom to focus more on the data. Of course, you can always use our API to control things like CI/CD flows where you need that automatic integration and the UI is not right. Workflows is also deeply integrated in the Databricks Lakehouse platform. That means that our users don't have to switch back and forth between tools. All the platform features are natively integrated and can be used easily, especially all the security features that your enterprise requires, including Unity Catalog. And of course, we're bringing integrated monitoring and alerting to these asynchronous workloads. You get all the benefits from tool consolidation on one unified, holistic Lakehouse platform without the need for a lot of toil or dedicated infrastructure. And Databricks Workflows is a fully managed service that lets you, again, focus on your data, not your operations. We've been running the largest orchestration service on the planet, so a major focus of our team has been and needs to continue to be stability at scale. So much so, I have to zoom pretty far in to see that it's only 3.5 nines right now. We've been improving that underlying service for years. It's now handling cloud incidents and limitations every day smoothly, shielding your critical workloads from disruption. But enough about words. Let me move to my demo. Okay, I'm going to start out this demo the same way all of you start your day, by opening up my Slack messages. The first thing I see is that I had an issue last night. I can easily see exactly what the error message is, exactly which workspace, job, run, and task were failed. I see their names, I see their ID numbers, and links directly to all of them, as well as important information about when that run started, how long it went, and how it was launched. And I can click directly through to the job run that was involved. Without going into too much detail at the job itself, what I see is that the top center task in the DAG, shark sightings, failed. It has a red bar on the top. Everything below that is light pink, and that's because it was skipped, because it needed a dependency. And on the right side, I see some more details about exactly how it was run. But I'm going to skip straight into repairing that job run, which includes everything you need to pick up where you left off and nothing you don't. So those successful tasks aren't even there. On the right side, I can also add parameters if I need those to make this run successful. In this case, I would normally just click Repair Run and have the run pick up where it left off. Instead, I'm actually going to take you on a deeper tour of this job first, so I will click Cancel, and then I'm going to click back and show you what this whole job was about. Looking at this job view, it looks a lot like the run view. The center is a DAG of tasks, and I'll go into what each of those are doing in a second. On the left side, I have a palette of additional tasks I can add, including notebooks, jars, and Spark submits, your old favorites. Some newcomers like Delta Live Tables, Python Wheels, DBT, and SQL. And then on the right side, I have some more details like creator and run as, and some other settings like the schedule. What's this job actually trying to do? Obviously, it's predicting shark attacks. It's ingesting files in the weather data. It's scraping APIs and shark sightings and reef data. It's going to combine all of those with a Delta Live table, check for drift, retrain that model, do some batch inference, and let everybody know what's going to happen to the sharks in the next day. The other thing that I notice about this task is some of this I've been told by my friends like Casey don't need to happen every day. You only need to retrain if drift is detected. So I've added a task parameter there in the small green box so that retrain is actually conditional. And it only runs a couple times a week right now. And this is what I mean by orchestrating the lakehouse. I've pulled together a variety of different tools to solve your actual problems, and I'm doing that efficiently using a single automated job cluster that I create and terminate on each job run that isolates your workload from disruption and minimizes startup time and cost by reusing it across all of the tasks. But what this job really needs is a dashboard. I've already coded that up in Databricks SQL, so I'll just drag a SQL task onto the canvas, and I'll look for a SQL task of refreshing a dashboard rather than executing the query or refreshing the alert. I'll look for my dashboard about sharks. There it is, predicted sharks. And then I'll drag in the dependency between batch inference and dashboard. I could have also done that in the right side panel by just selecting it in that drop-down. And then create task. Now my dashboard is going to update every day when this runs. And this could indeed run every day. But let's talk about some of the other scheduling options. Now, a daily schedule like that is perfect for predictable batch time-based execution, and it's an excellent way to use autoloader. But we can also use the new file arrival option. And what that will do is start up the compute only when a new file is detected. That'll be much more efficient for things where the delivery is not consistent or predictable, but you want moderate latency and minimum cost. And if this had been a streaming task, I would have used the continuous option that I'll show you now. And that minimizes all of the options you need to set in order to make sure that everything just runs as you need it to. Now that I've done all that, I'll click Save. I'll actually cancel out of the error, cancel out of the schedule option. And then we can run this now manually as well, of course. But let's take a look at how this job has been doing recently. I'll do that by going over to the Runs tab and taking a look at our matrix view. The columns here represent the task duration time from the past several runs, and we see that it's been mostly successful, except for that last run that we already talked about. And you can also see that there's a row here for each of the different tasks. The dashboard task, of course, hasn't run before because we just added it. And that retrain task, as I described, seems to be running once or twice a week, about what I'd expect. I think that's everything I want you to know about predicting sharks for the Dutch Coast Guard. So now let's take a look at a slightly higher level and go to the full job run view for my workspace. What I see here is that last night was pretty successful. There were 2,100 successes, only 21 failures. Those failures are only 21 failures. And then on the right side, what we see are the top 5 error types include some library installations and a few cancels, manual cancels. I can filter to the failed runs by going ahead and clicking on that top bar, and that will filter the table below. And then I can see that it looks like Ned is testing out a WSFS job, and I should talk to him about why he's having some trouble getting his test jobs to run. And I can also take a look at how those failures were spread out throughout the last couple days. It looks like there's not too much clumping there, so no specific incidents I need to diagnose or be concerned about. Across the top bar, I have some additional options I don't have time to show you today, including active runs and running late. And that will help you find those runs that aren't finishing when you expect them to, where you need to take a closer look and possibly intervene before they finish. Hopefully, that's given you a taste of everything that workflows can bring to you, and you're excited to go try this out immediately. It's of course live on all 3 clouds, Azure, AWS, and GCP today. We're super excited for you to see that, and in fact, we've got some breakout sessions coming. Of course, Michael Armbrust will be up in a second to talk to you about Delta Live Tables directly, as well as a breakout at 11:30 with more people from the Delta Live Tables team. 2:05 today, the Workflows Jobs overview will talk about our upcoming roadmap. And tomorrow, early in the morning at 8:30, you can learn all about adopting workflows. I'm super excited to see all of you there. Thanks.
Please welcome Michael Armbrust, Distinguished Software Engineer, Databricks.
Good morning. I'm super excited to be here today, back up on stage, to talk about Delta Live Tables. Delta Live Tables is a product that we released just a couple of months ago that makes it dramatically simpler to do the task of data engineering. Now, why do you even need to do data engineering? Well, it turns out all data starts off messy. And in order to do all of the advanced analytics, machine learning, and AI that we want to do, we have to first incrementally improve the quality of the data so that it's ready for that. We need good data to get good results. But that pipeline that I just showed was way too simple. That's never what it looks like in real life. Instead, it's always a mess of different tables and tools. You'll find you need to add things like Amazon Glue for ingesting files, Datadog for understanding what's going on your clusters, CloudWatch so that you can track your cloud costs, orchestration tools like Airflow to run different things and rerun when there's failures, Azure Data Factory for data ingestion, maybe another orchestration tool like Oozie. And finally, you're going to have some users who only know SQL, and so they're going to need something like Synapse. And all of a sudden, this starts to get really complicated, and you find you're spending all of your time on tooling. And that's why we created Delta Live Tables. It's a system that allows you to build reliable data pipelines in a dead simple way. The key idea here is we wanted to dramatically accelerate ETL development by giving you simple declarative languages in SQL and Python. As you can see, these 2 lines of code, this is actually an entire data pipeline. It ingests a whole bunch of files, infers their schema, it does it in a streaming real-time fashion, and then it creates another dependent table that cleans that data to get it ready for consumption. The dependencies are automatically captured, and this is all you have to write. Another key idea here is we want to automatically manage the clusters and the infrastructure that you need to run these pipelines. And I'll talk in a little bit about some of the tools that we use to do that. Just because your SQL queries execute doesn't mean they're going to produce the right answers. So we've been thinking about data quality since the beginning of the project. We've actually built in special language features that allow you to declaratively describe what data quality means in your particular domain, and then the system can automatically let you know when the incoming data violates those expectations. And we give you tunable policies for how to handle those violations. And finally, since freshness and real-time data is critical, we unify streaming and batch in one simple declarative framework. As I mentioned, we released a couple of months ago into GA, and a ton of customers have already been using it. I want to highlight one example that I thought was really cool from Rivian. They're actually an automaker, and they do a bunch of telematics data. So they look at how different parts are failing in the field, so they can automatically do predictive maintenance and service on them. And in one case, they took a manual pipeline that actually used to take over 24 hours to execute, and they were able to bring it down into near real time, and it executes at a fraction of the cost. And we've seen many stories like this amongst our customers. But you might say, how is all of that possible? And that's why I want to take you through a couple of the new features that are coming down the line that are going to make it even easier to build production quality ETL pipelines. The first feature is advanced autoscaling. I can't tell you how many times people have asked me, how many nodes do I need to do X? Well, the answer always is, it depends. It depends on what kinds of transformations you're doing. It depends on how big the data set is. It depends on what your SLAs and your budgets are. And enhanced autoscaling is here to help you automatically make that decision. We tie deeply into not only the Spark scheduler, but also into the data sources that are producing data, so we know how much data there is to consume. We can then automatically pick when we want to add machines, if and only if they're actually going to help the performance of your pipeline. And when there's capacity that's not being used, we get rid of it immediately. And this is really powerful, because even if you were to sit down and tune your pipeline, spend hours getting exactly the right cluster size, then your data size changes, and you need to do it all again. Advanced autoscaling will automatically do that for you. Another really common problem that I see people struggle with all the time is tracking how data in their lake changes over time. Whether you're in a regulated industry that has to keep an audit trail, or whether you're a machine learning scientist who wants to be able to model reproducibility by getting exactly the data that you train the model on, tracking changes is a very powerful tool. This is a technique often known as slowly changing dimensions type 2, where you actually keep a history rather than updating in place. But implementing this by hand is quite complicated. You have to write big, complicated merge statements with outer joins and window functions. But in DLT, we actually make it just a simple declarative language. You just say, store it as SCD type 2, and we automatically take care of tracking changes to that table. So now you can see in this example, we have a table of cities, and we have the birthplace of Spark, Berkeley, California, but it's spelled incorrectly. So when we want to go and update that data, when a new item comes in with that corrected spelling, since we've turned on type 2 SCD, rather than update it in place, it's actually going to do all the bookkeeping to keep track of not only what the new value is, but what this value was in the past and the time periods where different values were present in the database. But now we move on to my favorite topic, which is incrementalization. This is something that all data engineers in the room, I'm sure, have struggled with. Let me start by explaining what I mean by incrementalization. So your input data is always changing. And a naive, simple thing to do, and when your input changes, would be to just recompute the entire table. So I get one new row here, and I recompute the entire table. Many people do this, and it's not wrong. In fact, it's a pretty powerful tool because it's idempotent. It's always correct. You can just run it over and over again. But it's obviously very costly. The ideal thing to do here would be to, when a new row appears, just transform that row and move it downstream. But how do data engineers do incrementalization? If you excuse me for a moment, I want to nerd out a little bit about some of the techniques that people do here. So the first one is the one I just talked about. It's appending new data as it arrives, but this only works when the query is monotonic. What does it mean for a query to be monotonic? A monotonic query is one where new data in the input will only ever produce new data in the output. It will never result in a retraction. This is a great technique for incrementalizing your queries when it applies. It's very efficient. In fact, when we do this, it's kind of like doing streaming without all the complexity of doing streaming. But it only works for these monotonic queries: selects, projects, joins, and it cannot handle any changes to the input kind of by definition. So there's a couple of other techniques that I see a lot of people use. Another very common one is partition recomputation. Rather than just have one gigantic big table, what I'm actually going to do is I'm going to break up the table into little partitions by some property of the data. For example, by date. So in this case, I've broken up both the input and the output by date. And so now when new data arrives or when data changes in one of those partitions, I can only recompute the output partitions where the input data has changed. And that's obviously dramatically more efficient. This is a pretty cool technique because now we're able to do aggregations and updates to the data, but it has some limitations as well. it requires that the output and input have exactly the same partitioning, which isn't always appropriate. And so that brings us to the final technique, which is really the last 30 years of database research on incrementalized maintenance of materialized views. Basically, the idea here is you can statically analyze a SQL query, and you compute exactly how the output is going to change given some input. And if you can do that, now when you have a change to the input, I can actually just produce this delta, how the data downstream is going to change, and I can merge that into the final data set. This is pretty cool. This can handle pretty complicated queries. In fact, like I said, there's 30 years of research on how to decompose queries and do this for more and more complicated types of SQL. It's able to handle updates, inserts, and deletes, which is pretty powerful. But merge is a pretty costly operation. You actually have to read the output table in order to rewrite it. Even with deletion vectors, which we announced yesterday, it's still not particularly cheap compared to just appending data. The other problem is it's super complicated to reason about. You almost literally need a PhD in databases to figure out which queries this applies to and what techniques you can use. So you might be asking yourself, how am I, as a data engineer, supposed to be picking the right technique? And it's actually really difficult. And that's why I'm incredibly excited to announce Enzyme, the first ETL optimizer. Enzyme builds on the Catalyst query optimizer, which is built into Spark SQL. Catalyst allows us to analyze these query plans that are doing your transformations for ETL, but we add a new magic trick to that, which is delta. The delta transaction log tells us how the inputs are changing, and it actually allows us to take those changes and transactionally apply them to the output. So what Enzyme is it's basically a layer on top of Catalyst that takes all of these techniques that data engineers already know. It automatically figures out which ones apply to a given situation, and then it has a cost model, which will decide what the optimal technique for updating those tables is. What this means is, given a wide variety of queries, Enzyme is always going to pick the right one. So in this example here, I ran a bunch of different benchmarks with a couple of different types of queries, some simple ETL, some time series aggregation, and a case where there were a large number of changes to the input. You can then see how long each different technique took to modify the downstream table. And what you'll notice is Enzyme always picks the lowest one. When it's simple ETL, it'll just do those streaming appends. When it's time series aggregation and partitioning makes sense, it will use partitioning. If the input changes so much that it's actually cheaper to recompute the table than to try and do a merge, it can even handle that case as well. So if you think this is pretty cool and you want to learn more, I encourage you to come check out our sessions later in the day. We have both a data engineering session that's going to talk kind of generally about doing ETL on Databricks, as well as a deep dive into Delta Live tables at 11:30. Thank you very much.